Okay, welcome to the cardiovascular system. So this is based a little bit on the 200-hour um, stuff that we teach in the courses for yoga teachers, but also it's a little mix of other things. So it's really good recap for some people, but it might be something new and a really good refresher for those that haven't looked at this in a long time. So we're going to understand how the cardiovascular system is, what it's made up of, what are the pieces, the anatomy. We're going to have a look at circulation. We're going to talk a little bit about the stroke volume and cardiac output. These are terms that are mostly used, I think, in medicine, but are good to know as they relate to general health and how practicing yoga or any type of movement or exercise can support our general health in terms of our cardiovascular system. And then a little video on blood pressure. And then we talk about exercise and blood pressure at the end. So quite a nice short session, but hopefully a nice recap for you. So let's have a look at the cardiovascular system as its parts come together. So we've got heart, we've got veins and arteries. That's the blue and the red. One's carrying oxygenated blood, the other one's carrying deoxygenated blood. We've got the capillaries, which are the tiniest elements of the cardiovascular system there. You see where they converge with each other. So you've got the arteries and the veins coming together in these tiny branches. Those are the capillary beds. That's where the exchange happens of all of the good stuff that comes in from the oxygenated side or the red side, and then it collects from that side to take it out. So on top of that, we've got blood, around about 5 liters of blood. And in this closed system, that is always circulating around. So it's considered one closed system, although it's two loops. We've got the venous loop and the arterial loop. So we transport fluids around the body, nutrients. So it's not just, we think of blood, and I often explain to people when we want your injury to get better, we want to get blood flow to the area within reason, because we can also bring too much to the area. And that's not just for cellular respiration or the energy in the cell to get your, processes and physiology to work in your body, like blink your eye, salivate in your mouth, pump your heart. We also have other things in the blood which help, like nutrients. So we bring things like it can be the immune cells that come and help fix and help to rebuild areas, and other tiny parts that float in your cardiovascular system that go into the tissues and help with the general health of the tissues. And then we return the waste products as well through the same system. So in that lovely capillary bed, we then take all of the waste products and they get transported back to the heart. We also have the lymphatic system, which is a beautiful system that also helps with the fluid control. So we have a little bit, sometimes too much fluid coming out into the interstitial or between all of the cells area. And the lymphatic system is also there to take some of that fluid. And the lymphatics, we know of the lymphatics and think of the lymphatics as an immune organ or an immune system. And that's because it does also take the fluids back through the lymph nodes, which will then deal with any pathogens or nasty things that are in the blood. And then it will put the fluid back into this circulation via the vein up near the shoulder. So you've got that as well. Normally we have the lymphatics in green. They're not part of this system, but they work very closely too. So it's a closed system, as I said before, and it communicates with our respiratory system. So that means that we get a lot of the stuff that we need in the blood from, like the oxygen, we get that from the lungs so that we breathe in. And as we breathe in, we actually use our muscles to create a vacuum, and the muscles then vacuum and suck the air into the body, into the lungs. And we have the capillary beds where the vessels are picking up that fluid with containing all of that oxygen, and then we're dropping off the waste products as well. And that's happening with the respiratory system. So if there are any married couples in the body, definitely the cardiovascular system is married to the respiratory system. And you could call the lymphatic system their love child if you wanted to. So tissues require blood, oxygen to live. So mainly it is about the oxygen, but there are other nutrients that travel immune cells and immune fighting stuff as well. We'd have about 3 to 4 minutes to live without that. So blood supply is really important. The cardiovascular system is divided into pulmonary, systemic, and coronary. So the pulmonary is between the heart and the lungs. The systemic is everywhere in the body outside of the heart. And the coronary cardiovascular system is that of the heart itself. So the heart in itself is a tissue, cardiac tissue. So it needs its muscle tissue, sorry, cardiac muscle. It needs its own blood supply. So it's actually got its own little system as well. So the heart beats around 2.7 trillion times in our lifetime. And it's controlled by the autonomic nervous system. So we have the vagus nerve, which is going to be telling the heart to slow down. And then we have, and that's part of the parasympathetic nervous system, the two branches. The sympathetic nervous system is going to tell the heart to beat faster. That one doesn't have a special name. Most of the autonomic nervous system is just sympathetic and parasympathetic, but we have this wonderful name, vagus, for that main wandering nerve that gives parasympathetic action to most of our organs. So the heart is going to be speeding up when we need more action, sympathetic, and slowing down when we need to slow down, perhaps when we're resting, digesting, all of that stuff. So fight or flight, rest and digest, you might know it as, that is directly affecting the beats of the heart. And we can measure that. I think you may have heard of heart rate variability. So HRV is actually looking at the space between the beats. And what we take from that information is between the beats, how well is your body, is your nervous system moving between sympathetic and parasympathetic? So speed up, slow down. And believe it or not, a healthy human being will move between the two states in 1 minute many times. So a healthy HRV is one where it does go between sympathetic, parasympathetic, sympathetic, parasympathetic, speed up, slow down. And that's because we need to be reactive. We need to be reacting to what's going on around us. So you might be sitting having a cup of tea, and that might be quite a rest and digest thing to do. And then somebody will ring the doorbell, and you need to stand up. You need to pump a few more milliliters of blood to those muscles that need to get you out the chair. So that would be a sympathetic drive to get you out the chair. And then you say hello to your friend, sit back down. You want to move back into that rest and digest. So you want the heart to be reactive to its environment, and we don't want it to be stuck in one state or another. There are a few medical conditions where people's heart rate is affected. I think anemia is one which I'm very familiar with. And there are, I don't know, I think it's thyroid issues, I can't remember, but there's medical conditions that will affect your HRV. Actually, having anxiety, ADHD, those types of things as well can affect how the heart gets messages, and it might be a little bit faster or a little bit slower. And then, of course, people who have done a lot of exercise and cardiovascular exercise, they develop a very low heartbeat. And that's not really a direct result of just the autonomic nervous system. It's also actually a direct result of the heart muscle becoming more effective, which we'll look at in a moment. So the heart is our vital pump, a strong muscular organ that beats 100,000 times a day, pumps blood through the body to deliver oxygen and nutrients. It has 4 chambers, so 2 atria, or they're called atrium if we're just looking at one, and 2 ventricles. They're like a V-shaped, larger area at the bottom, a chamber that's more long and a little bigger. And here's a picture of some cardiac muscle. So cardiac muscle, just like the smooth muscle, looks a little bit different under the microscope, where our skeletal muscles are designed to be in long fibers to give us like lines of force. This heart is very different. It doesn't need to be lifting away from the body, anything like that, like a normal skeletal muscle would do. It is designed to pump and squeeze, so therefore the shape of the muscle fibers is suitable to that. So here's a little picture of your heart. So you might remember this from your training. This is looking at someone's heart who's standing opposite to you. So we would look at, to us, this is actually the left, but to the person who's standing in front of you, it's the right. So you'll always see the heart anatomy like this. So here we have the superior, we're going to go on a little journey. We have the superior vena cava vein. So in blue, that means that it's deoxygenated. So that's the largest vein that's coming back from the body. So it could have been anywhere in the left arm, down the legs, it could have been around the organs. Those tiny veins have brought all of that fluid back to the main kind of headquarters, which is the vena cava that comes up through the abdomen. And the superior vena cava is coming from more the head and neck, and the inferior vena cava, I should say, I've just mixed that up. So inferior vena cava is more for the body, and the superior vena cava would be head and neck. So either way, the blood's coming in from the body, and it comes into the right atrium. It drops through this valve here, the tricuspid valve, into the right ventricle, and that is a no return valve. And as the heart beats, it pushes it up through the pulmonary artery and it goes to the lungs. The lungs will do the exchange, and the exchange will happen. We'll exhale the carbon dioxide and any other waste products. And then as we've breathed in, we'll bring fresh new blood through the pulmonary vein to the left atrium. So if you are an attention to detail person, you're probably thinking, why is it called pulmonary artery, which is supposed to be the oxygen rich? It's the red in the body. So if you look at the whole cardiovascular system, the red are the arteries, and they are oxygenated. So why is it called pulmonary artery if it's deoxygenated going to the lungs? It's just the way it is in the heart, because there's a rule where anything going away from the heart is artery and anything coming into the heart is vein. So that rule has superseded the other rule, which is arteries are oxygenated, veins are deoxygenated. So it's only here. Everywhere else in the body, your veins are deoxygenated and always illustrated as blue. They're not really different colors in the actual body. And oxygenated blood coming away from the heart to your lovely bicep to give you that curl are going to be red. Just the other way around, only here in the heart. So lovely oxygenated blood's coming through pulmonary vein into the left side. So left side of the heart is all juicy red blood ready to go back to the body. So from the left ventricle, big squeeze, nice big thick lot of muscle here, big squeeze up through the aortic valve, and it goes up. Here we have the choice to send it up to the head and neck or down, and it goes down behind the heart and then into the body and everywhere else. And so that is how we circulate blood. And it's very interesting to learn about this stuff. We don't really need this on a daily basis as yoga instructors, but you do often get students coming in and giving you quite a detailed medical history about their left-sided heart failure, or I've had an aortic stent or something like that. And then you can kind of in your head, you're roughly involved then in the conversation, even though you're not going to advise on it. And you've got that basic knowledge of the heart, which is really nice. I would say this is my favorite system. I always say lymphatics as well because I think they're kind of so closely related. It's a great system to learn, and we can do a lot with the cardiovascular system in terms of learning how certain lifestyle approaches and exercise therapies really help with our blood pressure and cardiovascular health. So, arteries. We're going to do arteries and veins and just have a look at the two. So they are blood vessels that carry blood away from the heart, typically oxygenated. They have thicker muscular walls to withstand the high pressure of blood being pumped from the heart. Arteries branch into smaller arterioles, like this over here, and then into capillaries right at the end. We saw that on the previous picture, which are the smallest blood vessels. So the arteries have a little bit of a capacity to contract. So there's like 3 layers of muscle. It's all smooth muscle. So of the 3 types of muscle, skeletal, cardiac, smooth, it's the smooth, very similar to the cardiac. So they have a little bit of an ability to move the fluids along, but also they obviously need to be thicker to withstand the pressures going through them. So we don't need necessarily movement in terms of, if I want my arm to get blood supply, I don't need to make sure I hold my arm down and shake it out to get the blood there. It will make its way there, obviously, also due to the pressure being created by the beat of the heart. Whereas we'll see in a moment, it's different with the veins. Veins, they return the deoxygenated blood and normally come into the heart. They rely on muscle and movement. They have some smooth muscle in them. It's less than the arteries. So it's important with veins to think about how your lifestyle, your movement supports the venous return to the heart. So inside each of the veins, it does look a little bit different to inside the arteries. We have these little no return valves, just like you had in the heart. And these little valves are there to stop the fluid from going back down once it's been moved up. And if you think about the leg as the best example, so if you're standing all day and you're not really moving your legs very much, you're going to get quite a bit of blood pooling or staying quite low in the system. So when we move our ankles using our calf muscles and that kind of thing, we actually support the return of the fluid back up the body. It does, it will move itself a little, but then it heavily relies on arm movement. That's why it's kind of a recipe for disaster when we go on a long haul flight because you're very dehydrated, you're sitting for a long time, you're not moving, and so they often tell you to do those pedaling of the ankles, or at least get up and walk around, and that's literally due to this here. So no return valves. We want to pump the fluid back up. So legs up the wall, really nice. I often include in my yoga classes at the beginning a little bit of pedaling out the feet, or I just put them on a block or a pillow or something so their legs are up in the air, lying supine. And we just stretch out the feet and we just pedal, just pedal. So your gastrocnemius and your soleus, which make up your calf muscles, are powerful venous return muscles. Those muscles really help return the fluid back to the heart. But gravity can also help a little bit. So legs up the wall or just legs dangling in the air, that's like a reverse dangle, is always really nice to do. A lot of people that come to yoga, of course, they come from, I don't know, work, or they're standing a lot or driving a lot, and that goes for many people, I guess, across all age groups these days. So it's a really, really good thing to get some venous return in the beginning of your yoga class. The general yoga asana class will also support this. If you did warrior threes, if the simple art of movement is going to help as well. It's just giving that extra little bit if you do the targeted legs up the wall stuff. Okay, so your cardiovascular system is around about nine. This is one of those useless facts that is just really good to share, but just good to know. But I love it. But you can't really do much with that fact because we don't think we'd ever try and take it out of your body to see how many miles yours is. 95,000 kilometers long. I did a video once. I think it was like you can, your cardiovascular system could go round the world 5 times. Maybe it was 10 times, I can't remember. 7,500 liters a day flow around the body. So you've only got 4 to 5 liters, but 7,500 liters go around the body all day, which is pretty cool. It's quite a lot of work happening every single day. So let's have a look at what happens at the tissue level. So we talked a bit earlier about the exchange that happens both in the lungs, but it also happens in the tissue. So if we think about it's very easy to say just bicep muscle. You'll have capillary beds all over there, but you have them everywhere in the body. It is the way that the human body gives and takes its nutrients and waste. So in the bicep, you'll have a little capillary bed like this. And it's a little bit more like a gas exchange in some ways, but in the lungs, but it's diffusion if you look at the tissue level. So what happens is the gas exchange in the cardiovascular system primarily occurs through diffusion, where gases move from areas of high concentration into areas of low concentration. In the lungs, oxygen diffuses from the alveoli into the blood, while carbon dioxide moves from the blood into the alveoli. So if there's a high concentration in the inside at the end of the artery. It'll move into the outside. It'll move out of there and it will go to where it will then flow through and it'll get sucked back into the system. And you've got that little lymphatic branch of vessels that'll all be in between all of these. And the lymphatics are not a closed system, they're like little ends. So they'll all be weaved in between all of these little holes here, and they'll be there to collect extra fluids and take other things like pathogens back into their system and some of the excess fluids and take that to the lymph nodes and then on and back into the venous system. So just wanted to show you one last time the double circulatory system, which we've gone over already. So we've got our lungs. The pulmonary artery is going to bring in the deoxygenated blood. We'll take it back with the vein into the heart, pump it through the body. Then it gets to the tissues down here. It'll have its diffusion, and then it will drop off, pick up, take back through the vena cava. And on the way, you've got the lymphatics also dropping off into this system, back into the heart, back into the lungs. And that is the mammalian double circulatory system that we have as humans. Okay, so we're almost there. So a couple more slides. We've done our anatomy. We've looked at the circulation. We've looked at how the anatomy of the heart and how it supports the pumping of the blood. Let's go a little bit further now into general health and cardiovascular stuff. So your heart rate is beats per minute and somewhere between 60 and 80, depending on age, size, and medical condition. So if you're very, very healthy, 22 years old, you're probably going to have a resting heart rate of maybe lower than 60. Some people have a resting heart rate of 45. Some people, maybe you've got some health conditions, you're much older and you don't exercise, you might have a resting heart rate of 78, 80 beats a minute. So there's always a spectrum. We can't all be the same because not everybody is living the same with the same set of conditions. So the heart rate is in this little spectrum, and to be healthy, we want to obviously keep it as low as we can. There is a condition, I think it's called athlete's heart, where an athlete has trained the heart so intensely that it can actually have it beats so slowly and so effectively. Well, it's effective at first because an athlete will have an effective heart, but the athlete's heart can actually cause a major failure. So it can go all the way down to that lower end of the spectrum and have issues. We know that the upper end of the spectrum can also have issues. So that's the heart rate in general. The stroke volume is the amount of blood that we pump per beat. So it's an average of 70 milliliters. That's just an average. It's going to be different depending on your health as well, and depending on how much you exercise. Because if you exercise a lot, you're going to have a larger amount of blood pumping with each beat because your heart is bigger and more efficient at sucking in the blood from the system and pumping it back out. The cardiac output is the total blood pumped per minute. And that would be the heart rate times the stroke volume. So work out your cardiac output now and make a note of that. And I'll just give you a moment. You can also pause this if you're watching the recording. So just a reminder before I go and start this video, it's your heart rate, which you're going to need a minute or at least 20 seconds because you can times it by 3, times the average stroke volume, which is 70 milliliters, and that'll give you your cardiac output. Okay, so we're going to have a little look. I've been showing this video for many years, and of course I've tried to present it myself, but this video, 4 minutes, is so much better than me, so I've left it in this presentation. So the blood pressure is the force of blood pushing against the artery walls. It's measured in millimoles of mercury as systolic when the heart contracts over a diastolic, which is when the heart relaxes. So the systolic is the pressure when the heart contracts. That's the top number, and then there's a line, and the diastolic is when the heart relaxes. So that's the pressure at that point. So here we go.
If you lined up all the blood vessels in your body, they'd be 95,000 kilometers long. And every day, they carry the equivalent of over 7,500 liters of blood, though that's actually the same 4 or 5 liters recycled over and over, delivering oxygen and precious nutrients like glucose and amino acids to the body's tissues. All that blood exerts a force on the muscular walls of the blood vessels. That force is called blood pressure, and it rises and falls with the phases of the heartbeat. It's highest during systole, when the heart contracts to force blood through the arteries. This is your systolic blood pressure. When the heart is at rest between beats, blood pressure falls to its lowest value, the diastolic pressure. A typical healthy individual produces a systolic pressure between 90 and 120 millimeters of mercury, and diastolic pressure between 60 and 80. Taken together, a normal reading is a bit less than 120 over 80. The blood traverses the landscape of the body through the pipes of the circulatory system. In any plumbing system, several things can increase the force on the walls of the pipes: the properties of the fluid, extra fluid, or narrower pipes. So if the blood thickens, a higher pressure is needed to push it, so the heart will pump harder. High salt diet will lead to a similar result. The salt promotes water retention, and the extra fluid increases the blood volume and blood pressure. And stress, like the fight or flight response, releases hormones like epinephrine and norepinephrine that constrict key vessels, increasing the resistance to flow and raising the pressure upstream. Blood vessels can usually handle these fluctuations easily. Elastic fibers embedded in their walls make them resilient. But if your blood pressure regularly rises above about 140 over 90, what we call hypertension, and stays there, it can cause serious problems. That's because the extra strain on the arterial wall can produce small tears. When the injured tissue swells up, substances that respond to the inflammation, like white blood cells, collect around the tears. Fat and cholesterol floating in the blood latch on too, eventually building up to form a plaque that stiffens and thickens the inner arterial wall. This condition is called atherosclerosis, and it can have dangerous consequences. If the plaque ruptures, a blood clot forms on top of the tear, clogging the already narrowed pipe. If the clot is big enough, it can completely block the flow of oxygen and nutrients to cells downstream. In vessels that feed the heart, that will cause a heart attack when oxygen-deprived cardiac muscle cells start to die. If the clot cuts off blood flow to the brain, it causes a stroke. Dangerously clogged blood vessels can be widened by a procedure called an angioplasty. There, doctors thread a wire through the vessel to the obstructed site, and then pass a deflated balloon catheter over the wire. When the balloon is inflated, it forces the passageway open again. Sometimes a rigid tube called a stent is placed in the vessel to help hold it open, letting the blood flow freely to replenish the oxygen-starved cells downstream. Staying flexible under pressure is a tough job for arteries. The fluid they pump is composed of substances that can get sticky and clog them. And your typical healthy heart beats about 70 times a minute, and at least 2.5 billion times during an average lifetime. That may sound like an insurmountable amount of pressure, but don't worry. Your arteries are well suited for the challenge.
There we go. So we've got just two more little slides to do, and then we'll be done with this session, which has been all about the anatomy and physiology of the cardiovascular system, including blood pressure. So how does aerobic exercise make the heart more efficient? So we often say to people when you need to, reduce blood pressure and live healthier, you need to do more exercise. And we normally mean aerobic exercise. That's cardiovascular type exercise where we've increased the heart rate and we've worked the system, which we absolutely do in yoga. Although brisk walking, cycling, that kind of thing can be more intense. It's just on an intensity scale. So when we do that type of exercise, we make the heart work more efficiently. The heart becomes bigger, the muscle actually grows, and and the autonomic nervous system becomes a little better at switching between sympathetic and parasympathetic. Therefore, we teach the heart and the vessels to cope with pressure better. The pressure actually reduces. So when the heart becomes stronger, it can it can actually, and bigger, it can pump more blood per minute. So you get a higher stroke volume. Then, if you worked out your cardiac output on your new higher level of stroke volume, you'll see that you have a different figure as well, because it won't be 70 milliliters, it might be 80 or more. So more blood per beat means fewer beats needed to deliver the same oxygen around the body, which means a lower heart rate, and it improves all of everything above, all of the blood flow, the pressure in the system. The more efficient the more efficient heart reduces pressure on the entire system. And that is how aerobic exercise works with blood pressure. It's not a good idea if somebody has very high blood pressure. It's not a good idea to suddenly get them to run, because you might overwhelm the system. When we first start running, especially if it's something that we're not used to doing, we might actually go into a sympathetic drive, and the sympathetic drive might release certain hormones and chemicals that might actually constrict some of the arteries, and it would overwhelm. They might get chest pain, arm pain, or something like that if that were happening and it was going wrong. So when people go to exercise with high blood pressure, it's a good idea to start slow and build it up over time. Lastly, stress and blood pressure. Stress causes a surge of adrenaline, cortisol, and it makes the heart beat a lot faster. The blood vessels are tightening, and more blood volume is kept in circulation. What happens is the kidneys, when we go into a stressful, this is not the action mode that I talk about when we talk about exercising or writing an essay or getting out the chair and running to the door so you don't miss the post person. This is bad stress, toxic stress. And what the kidneys do in when we're in that stress state is actually we start holding on to fluid. So there's more blood volume in the system, and that can then make the blood pressure rise. So not only do we have more volume of liquid, we also have the stress chemicals tightening the vessels and causing a much higher pressure as it is. So this is where we come in with yoga. We can do lots of different physiological hacks in the beginning of our classes to help people's systems come out of that stressful state, especially if we teach in the evening. So it might be a 5 p.m., 5:30, 6 p.m. class. People might be running in from work. They are going to be carrying all of whatever happened in the day. That's obviously another generalization, which is always handy when teaching. It's not always the case for everybody. But they're coming in and they're going to, you start the class straight away. Let's go. Inhale, arms up, exhale, forward fold, and you do 20 sun salutations. I'm not saying Ashtanga, but very similar. This might, for some people, then create an environment where their body's already in the sympathetic nervous system. And they may have benefited from, and I'm just recommending it with this knowledge that we have of stress and blood pressure. It might be good to do some nervous system balancing breath, or just sitting and taking a bit of silent sitting. It might be good just to do that so that the people who are coming in the stress state have a better chance at those arteries relaxing. So I'm not saying that as a safety measure. I don't think someone's going to come into your class and because they're stressed, they're now going to have a heart attack. That can happen, and it probably would have happened anyway. What I'm actually really saying is, instead of it being a safety issue, this is more of a quality issue. We can add quality instruction to the beginning of our classes in case we have those stressed people that are coming in with the high cortisol and adrenaline in their bodies. So that was the cardiovascular system. Feel free to send any questions that you have. Thank you very much.